Hello everyone. Today we will continue with examples on the subject of first order and second order circuits, transients. But first I want to correct a mistake I made last lecture. The mistake was noticed by Ariel Futa. I'm sorry if I mispronounced your last name, but thank you for noticing the error. I was confused about the constant in the textbook and I thought it was a typo. Typos happen sometimes, but it turns out I made a mistake along the way. The mistake was as follows. So we reached this point here where we differentiated I. We have a formula for, we've calculated I first, right? Then we use the initial condition for I to calculate A1, the constant A1. And then we went back to the circuit and solved for VC. And then I opted to collect the sines and the cosines coefficients separately, right? So everything was fine for the cosines. So I took minus 6 times 4, which is 24, 3 times 4, which is 12, right? And then minus 4a2. So that was fine. But then for the sines, that's where I made the mistake. So I had minus 6a2, that's fine. 3a2, that was fine. But then for the sine, I should have had here minus times minus, I should have had plus 16. Okay, I treated the 4a2 as if it was the coefficient of the sine. Okay. So this was the error. This did not affect finding the value of a2, by the way, because when we apply the initial condition, VC at 0, sine 0 anyway goes to 0, right? So we still end up with only this equation mattering to find A2. So we still found the correct value of A2, right? And we have the correct expression for I, but how this mistake propagated is when writing the expression for V of C. When writing the expression for V of C, you just plug in minus A2 here, you get minus 24 plus 12, minus 12 plus 8, minus 12 plus 8 is minus 4. So this term was correct. But then here, the expression the constant should have been 16. Minus 6a2 plus 3a2 becomes minus 3a2. So that's 16 plus 6. 16 plus 6 is 22. Okay, so this constant should be 22 instead of 14. And now I remember it was in the textbook, it was set as 22. That confused me a bit, and I was getting 14, so I thought there was a typo. I must have missed that error. Okay, so thank you, Ariel, for pointing it out, and I just wanted to correct it. And all right, now we're going to move on to the example we started last lecture, which is an example of a pulsed input. So it's an example of multiple transients that we can solve using the techniques that we already know. So we have a voltage input V of t going into a 6 kilo ohm resistor, going into a 100 microfarad capacitor. We have Vc of t across the capacitor, and then we have another resistor, 4 kilo ohms. Then we have an 8 kilo ohm resistor. And then we're solving for this voltage, VO of t. Okay, so this would be first order circuit, and there are two transients here because the input is a pulse. So there's a change in the circuit in terms of the change in the input voltage that happens at time equals 0, and then another change that happens at time equals 0.3. Right, and the pulse, the height is 9 volts. Okay, so the transient happens at t equals 0 and t equals 0.3 seconds. Right, so we should expect at t equals 0, we have some initial condition, then some transient would happen, and then at t equal 0.3, we get to some value. We use that value as our new initial condition, and then a new transient will happen until it settles, and then we have, of course, the initial state here. Okay, so nothing new here. Everything is still DC. All the sources are DC, but using the tool of the step function, we can define like multiple instances where the voltage supply changes. And we want to solve for this using the techniques that we already know. Okay, we're solving for the output. That's the circuit variable we're solving for. This is a first order circuit. Right off the bat, we know that we can write it as what? As VO of t equals K1, right, plus K2 E minus T over tau. This is the general form of the solution. Okay, so this is the general form of the solution, and we want to find this for the transient that happens at t equals 0. So we're going to solve this for t. So there's a transient that occurs in this region. Let's call it t1, and then there's a transient that occurs in t2. So we want to solve this for the transient that occurs when t is larger than 0 and less than 0.3. And then we want to again solve later for when t is larger than 0.3. Okay, but let's solve for this transient first. Okay, and again, the continuity here applies through the considering the capacitor to be an open circuit. So for t less than 0, assume that the circuit already reached steady state a long time ago at minus infinity, right? So if I redraw the circuit with an open, that circuit will have a zero voltage source. The capacitor is an open circuit, right? And then I have a resistor here, a resistor here, right? A resistor here. I mean, nothing new here. The capacitor voltage is going to be 0. VC at 0 minus equals 0, right? And right. So that means, what does that mean in terms of the output voltage? VO of 0 minus equals 0. Okay. Now that doesn't mean VO of 0 plus equals 0, because remember we said only the capacitor voltage is continuous. Any other state variable is not necessarily, circuit variable is not necessarily continuous after the transient. Okay, so what happens when t goes to 0 plus, right after t equals 0? Let's draw the circuit, right? In this case, the capacitor is still a short circuit, right? So we have this thing, we have 9 volts. This is just after t equals 0, and then, but the capacitor started with a charge of by the way, this is example 7.6, my mistake. Okay, so let me see if there's an initial condition. Is that the cap is not charged. And anyway, I mean, since the voltage is 0 at t less than 0, that voltage anyway is going to discharge the cap. The cap would have been discharged long ago. So the capacitor has an initial condition of 0. But at 0 plus, what will happen is that the capacitor will still maintain the 0 volt. It will appear as a short. And then we will have the other divider, right? So VO 0 plus will also be 0. Okay, so using that, we can instantly say that K1 plus K2 e to the power 0 is 1 equals 0. This is the first equation that allows us to solve for K1 and K2. To get the second equation, we need to find VO at infinity, and this is a tricky point. Pay attention here. We want to find what VO at infinity is going to be, assuming the second transient does not occur. Meaning that what would the VO at infinity settle at, assuming this second transient here, this second edge does not happen, right? Without the second transient, what would the circuit settle at? That will allow us to get the second equation to solve for K1 and K2. Solving for what volt the VO might be at infinity without the second transient, that doesn't mean that the voltage is going to reach that steady state. It's just we are just solving for what steady state it might reach, right? Yeah. At that steady state, the voltage is going to still be 9 volts. The capacitor is still going to be open, so we're going to still have resistor, right? Capacitor is going to be an open circuit, a resistor divider, right? And then the values are 6, 4, 8, right? 6, 4, 8. Again, this is a hypothetical steady state. The circuit will never reach that steady state because we will have another transient happening before we reach that steady state. But for the purpose of solving the equation, finding the form of the equation, we want to assume that the transient continues indefinitely until it reaches steady state, right? So from that perspective, we can find what the capacitor voltage is going to reach at steady state, but we don't care about the capacitor voltage in this case because we're solving for VO, right? We want to find out what VO is going to be at infinity. So VO at infinity is going to be just 8 kilo ohms. It's a voltage divider, right? Over 8 plus 6 plus 4, 6 plus 4 is 10, 18 kilo ohms, right? Times 9 volt. So VO at infinity is going to be, kilo ohm goes with kilo ohm. This becomes 4 over 9 times 9. This becomes 4 volts. Okay, so, and that allows us to get the second equation, right? So VO infinity equals 4 equals K1 plus K2 e to the minus infinity over tau, right? E to the minus infinity is 0. So I end up with the equation that K1 equals 4. So that means that K2 equals minus 4. Remember, because K1 plus K2 equals 0. Okay, so we already now solved. Well, there's one thing remaining we need to solve for, which is the time constant. After t goes to 0, after t goes larger than 0, what would the time constant be? The time constant, again, we have to find the Thevenin equivalent circuit from the perspective of the cap, right? So that's going to be, so this is the cap, that's going to be, the voltage source is going to be a short, that's going to be 6 kilo ohms. And then we're going to have 4 plus 8. And we need to find R Thevenin from that perspective, right? So R Thevenin is going to be 6 kilo ohms parallel 12 kilo ohms, right? Which is going to be 6 times 12, their product over their sum, 6 plus 12, which equals 6 times 12. 12 plus 6 is what? Is 18, right? So divide by 2, this is 3, divide by 2, this is 9. divide by 3, divide by 9 by 3 equals 3, divide 12 by 3, that equals 4 kilo ohms, right? So that means that tau, we know that tau equals R Thevenin C, so that's going to be 4 kilo ohms times 100 microfarads. So that's kilo times micro is millisecond, and 400 times 4 is 400 milliseconds, which is 0.4 seconds. Tau is going to be equal to 0.4 seconds. Now we know what the form of the circuit variable is going to be for t larger than 0. And remember, this is true up to t equal 0.3, because after 0.3 another transient happens which changes the solution. But for t larger than 0 up to the second transient, we now have the complete form of the solution. It's going to be, we found that k1 is 4, k2 is minus 4, so it's going to be 4 minus 4, I can take 4 out, 1 minus e minus t over tau. Tau is 0.4. Do I want to simplify this further? Put this in the denominator? I don't know. Maybe let's do that. So 1 over 0.4 is going to be 10 over 4 is going to be 2.5. So it's going to be minus 2.5 t. Okay. Now we want to solve, so this is for t within this region. Right. Now we want to solve for t larger than 0.3, the point where the second transient happens. And to do that, we need, actually, I think I said we don't care about the capacitor voltage. Yeah, we do actually care about the capacitor voltage, because the capacitor voltage is the thing that's going to be continuous after t goes larger than 0.3. After t transitions 0.3 seconds, the capacitor voltage is the only thing that's going to be continuous. So we want to know what the value of it is going to be at 0.3 plus and at 0.3 minus seconds. So we need to calculate VC. Can we calculate VC from calculating VO? Yes, we can, right? It's a voltage divider, right? So let's look at the circuit. Let me show you the circuit, right? This is VC, right? VC, here's where the capacitor stands. VO is always gonna relate to VC by the voltage divider rule, because there's these two resistors in series, right? So VOT is always gonna be, and what's the voltage divider? It's gonna be 8 over 8 plus 4, so it's gonna be 8 kilo ohms over 8 plus 4 kilo ohms, right, times VCT, right? So I know VO, and VO relates to VC through this voltage divider, so I can write VCT as just simply 8 plus 4, which is 12 kilo ohms over 8 kilo ohms times VOT. So luckily from VOT I can easily find VCT. I want to find VCT because that's the variable that's going to be continuous through the point in time of the second transient. Right? So this is going to be equal to, it's going to just be VOT times some constant. So that's going to be 6 over 4, which is going to be 3 over 2 VOT, right? So that means that VCT is going to be 3 over 2. So 3 over 2 times 4 is going to be 3 over 2 times 4, this is going to be 6, right? So it's going to be 6, 1 minus E minus 2.5 T volts. VC at 0.3, that's going to be what the value of the voltage of the capacitor is. That will be our initial condition, right? And that is going to, for initial condition for the second transient, that will be 6, 1 minus E minus 2.5 times 0.3 volt. And we need to calculate this. So firing up a calculator and calculating this gives us VC 0.3 minus equals VC 0.3 plus right after the transient, just equals 3.17 volts, right? And right, and we said that VO, we discovered that VO relates to VC just through a voltage divider. So VC is 3 over 2 of VO, so VO is 2/3 of VC. So VO 0.3 plus and minus. This is one of the examples where although VO is not a capacitor voltage because it's linked directly to a capacitor voltage through a voltage divider, it will also be continuous. That's not necessarily always true. So that also is going to be 3.17. It's going to be 3.17 times the inverse of the relationship. So it's going to be 2 over 3. That's going to be 2.11 volts. Okay, so after the second transient for t larger than 0.3, again we have a second order situation, right? So first order situation, so VOT again is going to be some new K1 plus K2 E minus T over tau. Tau is going to remain the same. Well, is tau going to be the same? Right? What happens after t larger than 3? The voltage goes to 0, right? But we still have the same resistors from the perspective of the capacitor. So tau will remain the same, which is 0.4 seconds, right? So VOT is going to be K1 plus K2 E minus 2.5 T, right? And VC at now we want to find K1 and K2, right? VC at 0.3 plus, we said we already found it, right? We found it to be 2.11 volts, but that equals K1 plus K2. This is an example now of a calculation where we're not doing it at t equals 0. So this exponential will not cancel out easily or reduce to 1 or 0. So this, we have to calculate the exponential. So this is going to be E minus 2.5 times 0.3, right? So that gives us the first equation. If we do the calculation, we will end up getting 0.11 equals K1 plus 0.47 K2, right? And then the second equation comes from taking t to infinity. So that gives me VO infinity equals K1. And how do we calculate VO infinity? Again, we look at the circuit. And we assume that the circuit reaches steady state, right? What happens when the circuit reaches steady state? Well, the circuit is 648, right? So at steady state, the capacitor is an open voltage, right? Is an open circuit. But the voltage also in this transient for t larger than 0.3, the voltage is 0. So the voltage is going to be a short circuit. We have a resistor here. We have a short circuit here we have the resistor divider. So this is a kind of circuit where the capacitor will fully discharge at the end. There is no voltage source, the capacitor is an open circuit. Everything goes to zero at infinity, because essentially what's happening, the capacitor is discharging completely. So that means VO infinity equals 0, so K1 equals 0. Okay, so we end up then with K2 equals 2.11 over 0.47. We can calculate that using a calculator. That will give me 4.49 volts. So that tells me now the form of the equation. We already found that K1 is going to be 0, right? And K2 is going to be 4.49. So we end up with VOT for t larger than 0.3 being 4.49 e minus 2.5 t. Okay, so VOT is going to be this equation. It's going to be the response to the pulse is going to be as follows. VOT, let me see, this equation for 1 minus e minus 2.5 t for t larger than 0, less than 0.3, and then 4.49 e minus 2.5 t for t larger than or equal to 0.3. Okay, and this will be the solution to this example. I expect the VOT to be continuous, because remember, VOT is like a voltage divider derived from a capacitor. The capacitor will always be continuous, have a continuous voltage. So I expect calculating VOT at 0.3, whether I use this formula or this formula, I'll get the same result. Let me fire up my calculator and see what I get. So so if I say 4 1 minus exponential, I'm using Mathematica, I'm not using a calculator in this case, minus 2.5, and then t is 0.3. Right, so if I do that, I get 2.11, right? So I get 2.11. If I use the first equation, I should expect to get 2.11 even if I use the second equation. So if I take, let me go back to Mathematica, 4.49, and I suggest you try that, and take exp times exponential minus 2.5 times 0.3. Yeah, I get to within, because I did some approximation here, I get a very close number. I get 2.12. So the only reason there's a difference is because I approximated this constant here. This was like 4.8 something, 9.7, whatever, right? But the equation is continuous. Okay, so those are approximately equal if I ignore the rounding. Okay, yeah, so this ends this example. Okay, now I want to go to the next topic, next chapter, which is AC steady state analysis. Right? So we want to now move forward away from only analyzing circuits with DC sources, and we want to be able to analyze circuits with kind of more general sources, and we're inch our way towards doing that by first considering circuits that have sources that are what's called alternating, meaning that sources that look like sinusoids, right? And we won't be concerned with transient analysis. So we won't be concerned with transient analysis for sinusoidal sources. We'll be concerned with steady state analysis, meaning if I have some kind of circuit and the input to the circuit is a sinusoid, I won't be considering what happens at t equals 0. How will the response settle and change until it reaches steady state? I'll be mostly concerned with what happens at steady state. If I take this circuit and I apply a sinusoidal waveform to it, source to it, and I let it be for a long time, what kind of response will it settle to? Right? What would be the response to this sinusoidal input at steady state? So the question of transient, or what would the transient behave like, will remain open for now. We will not try to solve that problem, but we want to investigate what kind of answers we can get or what kind of things we can say about the steady state response due to AC, what's called AC transients. Right? Although for historical reasons we call this AC in contrast to DC. Although DC means direct current, we use it to mean something more general than just a current. It applies to a voltage, so we can say a DC voltage or a DC current. Same thing for an AC. It means literally it means alternating current historically, but we don't use this description to only describe current. We use it in general to describe current or voltage. So we say an AC voltage or an AC current. Okay. So the basic function that we use to model mathematically AC signals to start our AC analysis are sinusoidal signals. Sinusoidal signals are just signals that we build from sine and cosine, the so-called basic trig functions. So those are the basic trig functions, right? So I could say like x of t, any general circuit variable, that could be a voltage source, current source, is xm sine omega t, or I could write it as xm cosine omega t, right? Xm is called the amplitude or the magnitude, and sine is a function that you feed it an angle, right? And it spits out a number, right? So the input to the sine needs to be an angle. So if this is t has time, if t has units of seconds, omega, which is called the frequency, right? Right? It's angular frequency. It should translate from seconds to degrees, right? So we of course use radians to represent angles. So omega needs to have units of radians per second, so that it can take the second and turn it into radians to feed into the sine function, right? The basic property of the sine function or the cosine function of a basic sinusoid is that it's periodic. It's a kind of periodic signal. And its periodicity is 2 pi. So if I take omega t plus 2 pi, I get x omega t, I get the same value. Taking any sinusoidal function and shifting it by an angle of 2 pi, right or left, gives me the same function. It is a periodic function. Expressing periodicity in terms of time, in general, I can express it this way. So it's x omega, and just looking at the time variable, t time plus t, where t is the period. If I shift in time by the period t, I should get the same function, x omega t. Here I expressed x as a function of omega t rather than just a function of t. Okay. So omega in this context is what's called the angular frequency. There's another way of expressing frequency, and that is by expressing the number of cycles per second, per unit time, essentially. So I look at my sinusoid, and it's periodic. I have a different number of periods, and I look within 1 second. This is my unit of time. How many cycles are there in 1 unit of time? That gives me another way of measuring the frequency. This is not called, this is in contrast to angular frequency, this is called frequency as cycles per frequencies, cycles per second. This is called frequency f in hertz. Right, so this is an alternate way of expressing the frequency, and it's simply 1 second divided by the period, right? So 1 divided by t gives me the number of cycles per second, right? So this is t. I take 1, I divide it by t, I get the number of cycles per second. So f equals, by definition, 1 over t. Using this equation, I can get the general relationship between the frequency in hertz and the frequency and the angular frequency in radians per second, right? How do I do that? Well, from the basic periodicity property of sinusoids, if I take the omega n, I end up with omega t equaling 2 pi, right? So I end up with omega equals 2 pi over t, but I know that 1 over t is f, so I end up with omega equals 2 pi f. And this is the general property between the frequency in hertz and the angular frequency in radians per second, and the period. Okay, so just to summarize, f equals 1 over t, omega equals 2 pi f, or omega equals 2 pi over t. Very basic properties of sinusoids. Sinusoids, by all means, sinusoids are not the only periodic functions, but they are the simplest periodic functions. Actually, using Fourier analysis, in particular the Fourier series, we can express any periodic function, like any general function, fx plus t equals fx, as a sum of sines and cosines, where the sum goes from 0 to infinity. Right? And infinite, we can express any Fourier analysis tells us that we express any general periodic signal by an infinite sum of sines and cosines. So in many ways, sinusoids are the most basic periodic function. They're very simple. They just represent rotations on the unit circle. You keep rotating on the unit circle, and the sine is the projection on the y-axis, and the cosine is the projection on the x-axis. Right? Another thing we can do with sinusoids is that we can shift them. Similar to any function, I can take any function and I can shift it by an angle. So this is called shifting by a phase angle. So I can write x of t as x of m sine omega t plus theta, right? And this shift is called a phase angle, right? So you shift something by a phase angle. How do I draw that? Let's say I have this sign, right? This is the sign. Typically, when I have f of t, and I have f of t plus let's say a, I have, right? What this means was f plus a means is that at t equals 0, I place f at the value of a. So essentially, ft plus a is the same function as ft shifted to the right, shifted to the left. Ft minus a is the same function shifted to the right, right? So that where f equals a coincides with 0, and where f equals minus a coincides with 0, right? So if I have, this is f, let's say ft, and this is the point a, and I have fa here, ft plus a is simply going to be the function shifted to the left. So it's going to look like this. And what used to be fa is going to be at 0. So f0 equals f old at a. Okay. Same thing here. I'm shifting by an angle theta, meaning I shift to the right. So it's going to look like something like this now, my sign. Right? Okay. Some nomenclature about phase shifts. I could have like two signals, x1 equals xm1 sine omega t plus theta. It's shifted, this sinusoid is shifted by a certain angle. Then I can have x2 xm2 sine omega t plus phi, another sinusoid shifted by another angle, right? So we typically, we can say if theta larger than phi, let's say, it doesn't have to be, it could be smaller, and then we'll say the same thing, but it will be negative, right? We can say that x1 leads x2 by an angle of theta minus phi radians, right? If theta equals phi, we say that the sinusoids are in phase. This is another piece of nomenclature. If theta does not equal phi, something you see people say is that they are out of, the signals are out of phase, the sinusoids are out of phase. You should be aware of those phrases and what do they mean, right? In this course, we will mostly be expressing angles in radians. So if I say xm sinusoid, if I express the sinusoid as xm sine, the magnitude, sine theta plus pi over 4, let's say, I express the angle in not theta, omega t, right? I express the angle as radians always, because omega t is always in radians, because omega is radians per second, right? But as a shortcut, I could write something like this. I could say sine omega t plus 45 degrees. I could express the angle in degrees, and from context, you should understand that this is expressed in degrees, but really it should be in radians. Because on the face of it, this doesn't make sense, because I'm adding degrees to radians. This has to be radians because omega is rad per second times second. This is radians. I cannot sum two signals or two numbers with different units, right? This doesn't make sense. But from context, you should understand that this is just a shortcut. Sometimes we could write the angle in degrees because it's easier to understand, right? But mostly, I encourage you to stick to writing angles in radians. If you see in electrical engineering, it's very common to sometimes use degrees. If you see that, you need to understand what that means from context. You know, we know how to convert from radians to degrees, right? So pi over 4 is 45, pi over 2 is 90 degrees, pi is plus 180 degrees or minus 180 degrees. typically the formula is as follows. If you have an angle in radians, you divide it by pi. So this is the angle in radians. You divide it by pi, you multiply it by 180. That's all it takes, right? If you have an angle in degrees, you divide it by 180 and multiply it by pi. I mean, it's a simple proportionality transformation, right? We don't have to do that. We could just have done like theta times over 2 pi times 360, right? Or we could have done theta in degrees over 360 times 2 pi, same thing. Okay. Some identities to help us work with sinusoids, compare sinusoids with each other, figure out the phase shift or how much a sinusoid leads another sinusoid, and so on and so forth, is the following. So if you have minus cosine omega t, we don't like to have sinusoids with negative magnitudes. We'd rather compare sinusoids that have the same sign of the magnitude. So it's easy to convert from negative to positive. A negative sinusoid is just a shift by 180. So this equals cosine omega t plus or minus 180 degrees. Why? Because if I have like a cosine, this is how I draw a cosine. If I shift it to the right by 180, to the left by 180 degrees, or I shift it to the left by 180 degrees, meaning I shift this peak here, or I shift this peak here, I will get the same signal. It doesn't matter if I shift by plus 80 or minus 180, right? Same thing, minus sine omega t equals sine omega t plus minus 180 degrees. Of course, there's the basic property that we discussed when we talked about complex numbers, which is sine alpha plus minus beta equals sine alpha cosine beta plus minus cosine alpha sine beta, and then cosine alpha plus minus beta equals cosine alpha cosine beta minus plus sine alpha sine beta. Actually, one of the homework problems was proving those two basic identities using trigonometry, and then later some other problem asks you to prove it using the complex exponential. Right, so let's do that. Perhaps let's do that, and that will be like your reference for the homework solution. Right? I'll solve the other problems in the homework later. Soon, I mean this week. Bear with me. But let's prove those identities first. Okay. The proof is based on this geometrical construction. Okay, so let's do the construction. So I have the origin. I have a circle. Let me draw a circle. Let me use the tool to make drawing a circle easier. Some big circle so that I have freedom. Okay, and then I have the center of the circle. Okay, and then I have 3 line segments, right? 1, 2, 3. I have the angle alpha. I have the angle beta. Okay, so okay, so I project, right? So this is point. Let me name the points. This is point A, point B, point C, point D. Okay, I project a line from point B towards AD that hits it at a perpendicular angle. So if I do this, and this is a 90-degree triangle, right? This is angle beta, this is angle alpha, right? So of course this is a unit circle. So the radius r is 1. Okay, so what happens when I using this triangle? Let me call it A, B, C, D, E. Let me call this point E. So looking at the triangle A, B, E, I can project the radius, the hypotenuse, into AE. So that is going to be 1 times cosine alpha plus beta. So this line segment is going to be cosine alpha plus beta. Right? And then I have another triangle here. Okay. Now I want to take the point B and project it, this AB line. I want to project the point B into the line CA. So I want to draw a line that intersects CA at an angle of 90 degrees. So this is 90 degrees. Right? I don't need to do this line actually from C to AD. From C to AD, I don't need to do that. Okay. Now and right now we want to move forward, right? So there is a basic thing we got a new triangle now. So let me call this point. So this is A, B, C, D, E, F. Let's examine FG, and this intersection is G. Let's examine triangle GBF. This is a right angle triangle, right? Okay, so the triangle GBF. One basic properties of all triangles is that the sum of the angles 1, 2, 3, so angle 1 plus angle 2 plus angle 3 is always equal to 180 degrees. Right? That's a basic property in geometry. Right? So if this angle, we know this angle equals this angle, right? That's also a basic property in geometry. If you have two lines intersecting, this angle will equal this angle, right? But alpha is going to be this angle plus 90 degrees, right? But also this angle is going to be this same angle plus 90 degrees. So this angle and this angle is going to equal the same thing. So this angle needs to be alpha. This angle, you convince yourself that this angle up here is equal to alpha. Because alpha plus this angle equals 180. This same alpha plus this same angle that's equal to this angle plus 90 degrees also equals 180. So from comparison, this angle equals this angle, and alpha is is there, right? Okay, so that means that this right? That means that this projection here is what? This line here, BF, is equal to what? Is equal to sine beta. Right? This is equal to sine beta. Right? And then what we want to do is we want to project the point F down to the line AD. So I project it this way. Okay, so right, so that's right. So this gives me another triangle FG H. Let's call this point H. That gives me another triangle AFH. Right. Now what I can do is I can project AB into AF, and so what does that mean? That means AF is going to be cosine beta, right? And then I can project AF into AH. That means the whole AH is going to be again, what's the projection? The angle is alpha, so it's going to be cosine beta alpha. So this whole thing is going to be cosine beta cosine alpha. Okay. Right. So now what we need to do is we need to find what EH is, right? So that we can relate cosine alpha plus beta to cosine beta cosine alpha. So one more thing we need to do. Let me remove the 90 degrees from here. We draw this line, 90 degrees on the other side. I need to project from point F to line BG, right angle, right? Let's call this point I. Okay. Now this line IF is parallel to EH. So if I know the length of IF, I know the length of EH. IF is easy, right? IF is just the projection, the sine projection from alpha, right? So if the hypotenuse is sine beta, this line here, this segment here, BI is going to be sine beta cosine alpha, and this segment here is going to be sine beta sine alpha, right? So this segment here, EH, is sine alpha sine beta. And there you have it. We proved our first identity. So we said cosine beta cosine alpha equals cosine alpha plus beta plus sine alpha sine beta. So that tells me that cosine alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta, right? And this is it. We've proven the identity, the first identity. I use the evenness of the cosine, meaning cosine minus x equals cosine x to make this more general. If I have also a minus beta, I end up with cosine minus beta is just the same as cosine beta, and sine minus beta becomes minus sine beta. Sine is odd. Sine minus x equals minus sine x. So I end up with minus plus. Okay, minus gives me plus. So I've already proven this equation. How do I prove the sine identity? Well, let me erase this. Right. So I know BI is sine beta cosine alpha. I can also now solve for FH, right? FH is the same as IE, right? So FH, so this is BI, FH which equals IE equals what? Equals this line FA is going to be cosine beta, right? So this one is going to be cosine beta sine alpha, right? It's the sine projection, right? So and what about the whole line BE? BE is just equal to sine alpha plus beta, right? So BE should be equal to BI plus IE, right? So we've again proved now the second formula, that sine alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. So we've proved the second formula by looking at this line BE, right? So we proved that sine alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. And then we find it in general by using the even and odd property of the sine and cosine. So my cosine minus beta is just cosine beta. Sine minus beta is minus sine beta. So this becomes a minus here. And this is the second identity, right? So this is a very classic proof. You can find it anywhere, any textbook or online of those two identities. And it all goes back to Euclidean geometry. Okay. Hopefully this is clear, and if it's not clear, you can go back and try to follow it from the beginning. Right. In contrast, solving this for using the Euler's formula, the exponential form, is very easy. Right. So I just write EJ alpha plus beta. I use the exponential property. This equals AJ alpha times EJ beta, right? And then I just write cosine alpha plus beta plus J sine alpha plus beta equals cosine alpha plus J sine beta times cosine beta plus J, sine alpha plus J sine beta. And I just do complex number multiplication. I end up with the real part, which is cosine alpha, cosine beta, and then J times J becomes minus sine alpha, sine beta, plus the imaginary part, which is sine alpha cosine beta, this term with this term, and then this term with this term, plus cosine alpha sine beta. And all I have to do is equate the real part with the real part and the imaginary part with the imaginary part. I end up with cosine alpha plus beta equals my formula, right? So it's very simple to prove with complex numbers. We don't need to do all the geometrical analysis. And then sine alpha plus beta equals sine alpha cosine beta plus cosine alpha sine beta. And then I use the even and odd properties of the sine and cosine to find it in general. Right, so this becomes plus and this becomes minus. And that's it. That's the proof using a complex analysis. Alright, so that's it for this lecture, and we're going to continue with AC analysis in the next lecture. Thank you guys.